although we've already discussed somewhat about the importance of the concept of rate of change to calculus, I want to really focus on that here. There are lots and lots and lots of real-life applications of rates of change when you're studying physics with velocity and acceleration, population growth rates, unemployment rates, production of almost anything, those rates of change, water flow. You could go on and on and on, and how basic this idea of a rate of change is and how important it is. But here's an important thing to remember as we're doing these problems. When you're computing rates of change, you've got to be very careful about what you're being asked to compute, especially the need to distinguish between the average rate of change and the instantaneous rate of change. I like to think of the distinction between these two things in terms of what we talked about earlier with the slope of a secant line through 2 points on a curve versus the slope of the tangent line at 1 point. And just to remind you, these graphs are from earlier. The first two are illustrations of finding the slope of a secant line through 2 points on the curve. You can see they're both 2 points on that curve. And when you find the slope of that secant line, you're finding the average rate of change. So these first two represent the average rate of change. But as these 2 points get closer and closer together, as this delta x approaches 0, gets smaller and smaller, finally that second point falls right on top of the first point, and instead of having a secant line, you have a tangent line. And once you get to the point of tangency, the slope of the tangent line represents the instantaneous rate of change. This is an extremely important distinction. So think about that. When you're doing an average rate of change, you're just doing something you learned back in Algebra 1 and Algebra 2 in high school. You're finding the slope of the line between 2 points. So for average, you've always got 2 points. That doesn't require any calculus at all. By the time you get down the slope of a tangent line, an instantaneous rate of change, now you're talking about the calculus. And if you'll remember that the derivative is what we defined, or as the terminology we used, or as the word that we used to describe the instantaneous rate of change. Going back to the distinction though, when you're talking about the average rate of change, it's just algebra. It's just rise over run. Delta y over delta x, rise over run. It's just the change in the y coordinates. That's how much y changes between the 2 points. That's the rise. Over the delta x, which is the run, that's how much the x changed. Rise over run, delta y over delta x. And in terms of the function values, if you have a function f over an interval from a to b, in other words, the left endpoint is a and the right endpoint, the left endpoint is a and the right endpoint is b. So you're running from a to b, a on the left, b on the right. Is the change in the y coordinates? Well, if you're plugging into a function, one of the y coordinates is f of b and the other coordinates f of a, so the rise is f of b minus f of a. And then on the x-axis, you've got the x coordinates, the difference there is b minus a. It's strictly the formula for slope that you learned back in Algebra 1 and Algebra 2 of high school. That's the average rate of change. Before we get back to the derivative with the instantaneous rate of change, let me just talk a little bit more about it. Average. A common thing to do with rate of change when you're first studying it is to find the average velocity of some object that's moving in a straight line, and one of the most common straight line movements is just something falling. You'll see that a lot. In any case, the average velocity is just the change in distance over the change in time. It's like getting in your car and driving, and if someone asks you what your average velocity was on that trip, you would measure the distance you traveled and divide by the time. It's the change in distance over the change in time is your average velocity. Again, I said one of the most common applications of an object moving in a straight line is just letting something fall from some height. So this is what this example is. A free-falling object is dropped from a height of 100 feet. Neglecting air resistance, the height s, measured in feet, of the object at time t, measured in seconds, is given by the equation s is equal to minus 16t squared plus 100. So you're given that information, and you're being asked to find the average velocity of the object over each interval. Whenever you're asked for average rate of change, velocity is a rate of change, you simply find the slope, rise over run. They're asking us to do it, first of all, on the interval from 1 to 2, in other words, from 1 second to 2 seconds. So what's happening between 1 second after the object was dropped until 2 seconds after the object was dropped. It's just your same old slope formula from high school algebra, rise over run, delta y over delta x. You don't need a graph to figure it out, but I did throw something up there. If you drew the graph of this s function, you would get a parabola that opens down. And when x is, or in this case t, when t is 0, s is 100. So you don't have to have a really accurate sketch. In fact, you don't have to have a sketch at all to do this, but I thought it might be helpful. But you're just calculating the slope of the line that connects the 2 points where t starts out being 1 and it ends up being 2. Rise over run. That's s of 2 minus s of 1 over 2 minus 1. Remember the formula when you're going from on an interval a to b for a function f. It's f of b minus f of a over b minus a. That's the formula for the average rate of change. Now, I don't know if you want to call it memorizing it or not, but you need to be familiar with how to pop that right down from your brain onto the piece of paper. When you see average rate of change, that's your formula, but it's just rise over run. In this case, the function is s instead of f, but otherwise, and the interval is, instead of being a to b, is 1 to 2. So you plug in, you get s of 2 minus s of 1 over 2 minus 1. Well, how do you do that? Well, s of 2 is what you get by plugging 2. S of 2 is what you get by plugging 2 in for t. And that's this negative 16 times 2 squared plus 100. Then you want to do s of 1. Well, what's s of 1? S of 1 is what you get by plugging a 1 in right here in place of t. And that's where you get the negative 16 times 1 squared plus 100. And then it's over 2 minus 1, and obviously 2 minus 1 is just 1. Now it's just an arithmetic calculation. I will say, if you'll pay attention, you'll notice this plus 100 in the first expression is going to have a plus 100 in the second expression, and there's going to be a minus sign there. So if you're watching what you're doing, you might notice you could just cancel those 100s out and make your arithmetic a little easier. If you don't cancel them out, you'll still get the same answer, and it'll be correct, of course. But if you notice that, your arithmetic's a little bit easier. So now you're basically just squaring 2, which is 4, and 4 times negative 16 is negative 64, and then you're squaring 1, which is 1, and 1 times negative 16 is negative 16, but there's this minus sign right here too. So you've got minus a minus. You got to be very careful about these signs. That minus a minus makes a positive 16. So you've got minus 64 plus 16 is negative 48. You have to be careful, especially about signs. So the average rate of change of an object being dropped from 100 feet, if you ignore air resistance, from 1 second after it's dropped until 2 seconds after it's dropped is -48, and it's actually in feet per second. So you could, if you wanted to, add feet per second. Simple, right? How about this interval? Same question, same instruction. Find the average velocity of the object, but this time you're going from 1 to 1.5. Before we're doing 1 to 2. Process is the same. So without belaboring this, when they say average, you know you're going to do the rise over run. It's going to be S of the right-hand endpoint, which in this case is 1.5, minus S of the left-hand endpoint, which in this case is 1. So it's S of 1.5 minus S of 1 over 1.5 minus 1. Notice all we did is change what was 2 before to a 1.5 because that 2 changed to a 1.5. But otherwise, the process is the same. So you've got to plug 1.5 into the S function, you've got to plug 1 into the S function, subtract the results, and divide by 1.5 minus 1, which of course is going to be 0.5. I'm not going to belabor the arithmetic this time, but I will notice that the 100s cancel out again. If you notice that, the arithmetic is easier. You end up with -36 plus 16 over 0.5. And if you do that, you'll end up with -40, and again, the units are feet per second if you want to add that in there just for completeness. And now it should be old hat. Same question. The right-hand endpoint changed from 1.5 to 1.1, but the calculation is the same. It's still an average rate of change. You're going to do rise over run. The only difference is now you're using the right-hand endpoint is 1.1 instead of 1.5 or 2 of the A part. Plug 1.1 in for T, then plug 1 in from T, subtract the two results, and divide by 1.1 minus 1. The right-hand endpoint minus the left-hand endpoint. Well, 1.1 minus 1 is just 0.1. And again, if you notice those 100s canceling out, the arithmetic is easier. You don't have to notice that, but it certainly makes the arithmetic easier. And you end up with -19.36 plus 16 divided by 0.1. If you do the arithmetic there, you'll get -33.6. And again, if you want to put the units on there, that is feet per second. Average velocity, rise over run. Algebra 1 and Algebra 2 concept, no calculus involved at all. Now let's look at what we just did. We started out doing the interval 1 to 2, then we went 1 to 1.5, and we did 1 to 1.1. We're letting the left-hand endpoint stay at 1, and we're letting the right-hand endpoint get closer and closer to 1. So we're sort of looking at a limiting process. We won't do any more, but I will say that if you did keep getting y values, or not y values, if you kept getting b values, right-hand endpoint values, closer and closer to 1, although we're not going to do it, it turns out that these results get closer and closer to -32. You can just take my word for that. We're not going to actually do the calculations, but we could do from 1 to 1.01 and 1.1 to 1.001 and 0001, and you'd find out that you keep getting closer and closer to 32, and that tells us that the instantaneous rate of change, in other words, you're turning the secant line into a tangent line by pushing those 2 points closer and closer together. That turns it into an instantaneous rate of change. So the instantaneous rate is -32 feet per second. And again, this is something we learned before, but I just want to throw this up here just to keep reminding you. Whenever you go from average rate of change to instantaneous rate of change, you're taking remember we called this a difference quotient earlier, but it's basically rise over run. But we're taking the limit of the rise over run as the interval on the x-axis gets close, that gap gets closer and closer to 0. That's what we called a derivative. And it makes our life easier because calculating a derivative is something we learn some shortcuts for. We learn some formulas for the power rule and the constant rule and all those things. It's going to make calculating these derivatives actually very easy, which means we can do instantaneous rates of change fairly easily as long as we can do the derivative fairly easily. So our goal here is to use derivatives whenever we can, because if we can get the derivative easily, then the rate of change is very easy and you don't have to do so much algebra and doing all these rise over runs. That's kind of the goal of this process. We mentioned some of this physics stuff with dropping something, let it free fall, things like that. But another common application of rates of change are marginals in economics. And I know some of you are taking economics right now. But in economics, the economists talk about marginal profit, marginal revenue, marginal cost. They're rates of change. Marginal profit is a rate of change in profit of producing another item. The marginal revenue is the rate of change in revenue from producing one additional item. Marginal cost is the rate of change in cost of producing one more item. And if you're taking economics, this is a really good time to be talking about marginals in this class. The basic relationship between profit, revenue, and cost is given by this equation that you probably already know, that total profit is simply the total revenue minus your total cost. So if you're running a business, your profit is determined by your revenue and cost, and the difference between the revenue, which is how much you take in, minus what it costs you, is the profit. Anything left over is the profit. The difference between the revenue and the cost is the profit. And as I said, these are rates of change, so you can use derivatives to do them. That makes life nice, because if you've got a relatively simple profit function, revenue function, cost function, it will be simple to take its derivative, which means calculating these marginal values will be simple. So the marginal profit is the derivative of the profit function. So I wrote here dp over dx. You could also call it p prime of x. You know, we've got lots of notation for derivative. I sort of use them variously so you can keep them on the front of your mind as you're thinking about it. Of course, that could be written as r prime of x, and that marginal cost could be written as c prime of x. So these are all equivalent notations. dc over dx is the same as c prime of x. dr over dx is the same as r prime of x. dp over dx is the same as p prime of x. There are lots of different ways to write the derivatives, and I'm just trying to keep those different symbologies in your mind as we go through this. Let's do an example and see how simple this really is. Suppose the profit in dollars derived from selling X units of an alarm clock is given by P is equal to 0.0002 X cubed plus 10, where X is how many units you're selling and P is the profit in dollars. We want to find the marginal profit for a production level of 50 units. Once you understand what you're being asked to do, it's extremely simple. We know that marginal profit can be found by taking the derivative of the profit function. Well, you're given the profit function, so all you need to do is take the derivative of it. So remember, this is a polynomial, and we can do it term by term. So the first term is a constant, a number, times x cubed, and that means we can use the power rule. Remember what the power rule said? It says take the exponent and multiply it by the coefficients. You're going to take 3 times 0.0002, that turns out to be 0.0006, and then you're going to drop the 3 down by 1 and make it a 2. And then the derivative of 10x, we learned that as a separate rule. When you have a number times x, the derivative is just the number, so it's going to be 10. Or you can think of it as a special case of the power rule. So the exponent of 1 would drop down to a 0, which makes x to the 0 equal to 1, and you just end up with a 10 either way, because 1 times 10 is 10. I would just remember that anytime you have a constant times x, the derivative will be the constant. A little faster. But in any case, you get the derivative, and then you plug in 50. So at the production level of 50, you get 0.0006 times the quantity 50 squared, and then plus 10. So you got to square 50, multiply it by 0.0006, and then add 10 to it, and you'll get $11.50. So the marginal profit is basically how much profit you can expect from producing the next unit. So if you're producing 50 units now, what could you expect to get if you produced and sold a 51st unit? In fact, in the second question, they're asking you to look at that directly. Now it says to compare the marginal profit with the actual profit. In other words, the marginal profit here using the derivative is just close to the actual difference between those two. Just like the slope of the secant line is close to, but not exactly the same as the slope of the tangent line as the delta x goes to 0. It's the same idea here because we're using the derivative to estimate the marginal rate. We're using the derivative as a marginal to estimate the average rate of change in going from 50 to 51. So I guess another way to think about it is the first question involves calculus only. Well, it involves calculus, not only. The second involves algebra only. It does not involve any calculus at all. And as you get more and more into this, you'll see what I'm saying about this. We're using the derivative as a quick way of getting a marginal value or an instantaneous rate of change. It's an estimate of the average. And we're doing the average here, which is an algebra problem. So what I'm going to do is go from 50 to 51. So what I do is I plug 50 back into the profit function. If you plug 50 back into the profit function, you see you're going to cube that 50 and then multiply it by 0.0002, and then you're going to add 10 times 50. And that comes out, if you do the arithmetic, to be $525. And then you're going to plug 51 into the profit function. And when you plug 51 in, I'm not going to belabor the arithmetic. You need to practice that if it's something that you have trouble with. You'll get $536.53. So it's asking us to find the actual gain in going from 50 to 51. Well, we know how much profit you get from 50. We know how much profit you get from 51. So the difference in those two values is the amount you would get by producing that 51st unit. In other words, going up to you're sitting at 50, you go up to 51, you'll make an extra $11.53. And now maybe you can see better what I'm saying. You're getting an approximation when you use the derivative. $11.50 is about what you would expect if you actually went up from 50 to 51. In reality, it'd be $11.53. But $11.50 is pretty doggone close, so you'll take a derivative every time over doing all this arithmetic. It saves you from doing rise over run with all this arithmetic. And you're close. You're only 3 cents difference. So anytime you can use the derivative to get an answer, it's a lot quicker, almost always quicker, than trying to do the algebra, which involves all these calculations with rise over runs with numbers that may or may not come out really very nice. I hope I'm not confusing you by over-explaining, but once you get the idea in mind, you'll see what I'm talking about. These questions involving actual, which is like an average, that's going to be your average. The actual profit from going from 50 to 51 is just a rise over run. That's just plain algebra. It's rise over run. Versus the derivative way of doing it, which gives you an answer much faster. And the price you pay is not very steep because look how close those two results actually are. Okay. I'm going to let that go now and finally end by saying, note that the actual profit of $11.53 in going from 50 to 51 units is approximated by this marginal profit, which was so easy to calculate. That's the last time I'm going to say that for this problem. I'm trying to emphasize how much better doing it using the derivative is than using the average, which is a rise over run, which is typically a tedious calculation. To get an answer that's probably good enough. All right, how about this one? The last problem was finding a marginal profit. This is asking you to find a marginal revenue. If the revenue function is given by that polynomial, it's revenue in dollars from a fast food restaurant selling X hamburgers per month. Find the marginal revenue function. Well, again, marginal means derivative. So using the power rule, the derivative, or the special case of the power rule, if you will, the derivative of number times X is just a number. And then the power rule on the second term, you take the exponent times the coefficient, multiply. 2 times 1/20,000th is 1/10,000th, and then the 2 goes down to a 1, an understood 1 here. That's the marginal revenue function. Second part, what's the marginal revenue from the sale of 20,000 hamburgers? Well, X is the number of hamburgers, so you simply plug 20,000 in for X. Luckily, remember 20,000 is like 20,000 over 1, so you end up with 20,000 over 10,000 in that second term. Well, 20,000 over 10,000 happens just to be 2, so you get 3 minus 2, which is 1. So the marginal revenue from the sale of 20,000 hamburgers is $1. You could expect to make about $1 extra in total revenue in going from producing 20,000 hamburgers to producing one more, which would be 20,001. And you can see that that's going to be so much easier than had I asked you to calculate it exactly. You'd have to do the rise over run using 20,001, do that calculation and do 20,000. It would just be so much easier. I hope you can see that, doing it this way. The price you pay is an estimate, but it's going to be close. If the cost function is given by C of X equals 5,000 plus 0.56X, anywhere from 0 hamburgers up through and including 50,000 hamburgers, find the marginal cost of producing 20,000 hamburgers. Again, you should think marginal cost, derivative. Derivative of the cost function, the derivative of 5,000, that's just a number, is 0. And the derivative of number times X is just a number. So the derivative comes out to be just 0.56. There's no X in it. So the marginal cost function is a constant. What that really means is it's going to cost you about 56 cents per burger, no matter how many you're producing. So the answer is 56 cents for 20,000 hamburgers, but it's also 56 cents for 30,000 hamburgers, or for 10,000 hamburgers, or for 5 hamburgers. Whenever you don't have it, whenever there's no variable in the marginal, it just means it's the same for every value of X. So even though it's easy, you've got to think about what that means. When you have a constant marginal, that means it doesn't matter how many you produce. It's always going to be that number, no matter what number, no matter what value the X is. I want to sort of get to, as I'm getting to the end of this, I want to sort of illustrate the main ideas of what we've done so far, and then I want to end with one final example. Everything we've talked about today can be distilled into these main ideas. First of all, that the average rate of change of a function on an interval is just the rise over run. It's what you learned in algebra. It has nothing to do with calculus. The instantaneous rate of change, however, is a derivative, and that is calculus. That's what we've learned in this course up to now. And in particular, if we're talking about a position function, in the problem we've worked before, they used the letter S for position. There's no rule that says you have to, but it's very common in physics, I think, to use the letter S for the position of an object moving along in a straight path. But in any case, for the position function, in this case, we're calling it S, of an object moving in a straight line. That could be just dropping something, or it could be something moving along a straight track. The derivative, s prime, is the velocity of the object. So the takeaway here is the derivative of the position function of an object moving in a straight line is the velocity function. Then we learned that the profit is revenue minus cost. And we learned about the three marginals associated with that. If you take the derivative of the profit function, you get the marginal profit. If you take the derivative of the if you take the derivative of the revenue function, you get the marginal revenue. If you take the derivative of the cost function, you get the marginal cost. So derivative, profit, marginal profit. Derivative, revenue, marginal revenue. Derivative, cost, marginal cost. Let's end with one more example. Suppose I give you a function f of x equals the negative of x squared minus 18x minus 4, just a simple polynomial. Find the average rate of change over the interval from minus 9 to 1. Anytime you see average, you say, okay, I know there's no calculus here. I'm just taking rise over run. That's going to be delta y over delta x. So you take the, that's like in the formula, that's like the b and that's like the a. It's f of b minus f of a over b minus a. So it'd be f of 1 minus f of minus 9. That's f of b minus f of a in the numerator. And then the denominator is just b minus a. So it's 1 minus a minus 9. Be careful about these signs. Up top, you first want to calculate f of 1. Well, f of 1 is what you get by putting 1 in where the x is, and you'll end up with this. And then you want to calculate f of minus 9, and you go back up again and put minus 9 in for the x's, and you end up with this. The main thing is being very careful about the sign. When you square 1, it's going to be positive 1, but there's a negative sign in front of it, so that's going to be negative 1. So you've got to be really careful. Same thing here. When you square minus 9, you get 81, but there's a negative sign in it, so that's going to be a negative 81. And then when you get near the end, you've got to deal with that minus sign there, and be careful, very careful. Don't get in a hurry. This is why doing the instantaneous rate of change is so much more preferable. You don't get caught in all this arithmetic in general. I won't belabor this, but you need to make sure you can get negative 23 out of that first bracket, and you need to be sure you can get positive 77 out of that second bracket. And remember, there's a minus sign between them in the formula. And then, of course, minus a minus makes a plus, so you get 1 plus 9 in the bottom, which is 10. So up top, you get minus 23 minus 77, which is minus 100. Minus 100 divided by 10 is negative 10. So the average rate of change in that function going from minus 9 to 1 is negative 10. Now let's find the instantaneous rate of change at each of the interval endpoints. Well, anytime you say instantaneous, you know you're going to be doing a derivative. That's calculus. Sounds scary, but it's actually easier. All you have to do is take the derivative of this function. We've learned the rules. It's just a polynomial, so you can do it term by term. The derivative is the instantaneous rate of change. The derivative of minus x squared using the power rule is minus 2x, and the derivative of minus 18x is minus 18, and the derivative of a constant is 0. So the derivative is just f of x is equal to negative 2x minus 18. And it says find the instantaneous rate of change at the interval endpoints. Well, there are two endpoints. We have to do it for each one. So we want to do it for minus 9, then we want to do it for 1. It doesn't really matter which one you do first. I'll choose the minus 9. If you do minus 9 first, you just plug a minus 9 in for x. And again, you get a negative times a negative is positive. So you end up with 18 minus 18. You actually end up with a 0. So that the slope there is 0, which means the instantaneous rate of change at the left endpoint is 0. It said to do it at both endpoints, so we have to do it again. The other endpoint is 1. We plug 1 in here for x. You get negative 2 minus 18, which is negative 20. And I hope you can see that whenever you see average rate of change, it doesn't involve calculus to say, well, that's great, I can do this with skills I already have. That's true, but look how much arithmetic you end up doing. It's a little bit more tedious. You say, okay, instantaneous, that's scary because that means calculus. Well, it does, but when all is said and done, look how much easier the work actually was. So I hope you'll begin to appreciate how much it helps to be able to do this, the calculus. It makes your life easier in lots of ways. So be sure to get this work done as quickly as you can while it's fresh in your mind, and also get it done early enough to get a bonus, and also get it early enough to get help if you're having trouble.